Hi all and welcome to the video. Today we're going to be talking about representing algorithms on the GCSE Computer Science course under the AQA exam board. On the right hand side you'll see a reference to the official specification whereby you've got a column for content and another column for additional information, all of which will be covered in today's revision video. The first thing we're going to talk about is the idea of abstraction. Abstraction is a computer science term within the context of computer science, that I should say, that essentially forms one of the cornerstones of computational thinking. Its origin as a late Middle English word derives from a Latin term meaning to draw away, and we can define abstraction as being the process of considering something independently of its associations or attributes outside of a computer science context. But inside of the context of the course, we actually refer to it as the representation of a real-world object or concept using a computer program that thus removes any unnecessary detail in order to focus on what is most important, and that actually leaves us with really what is most important as well. When we think about examples of where we see abstraction in the real world, I've got three pieces of software here for you. First one being Microsoft Word, which if you really think about it is just an abstract or computing abstract version of the traditional pen and paper. Adobe Photoshop again is essentially just an abstract version of a picture or a photo that's been taken through some sort of film development. And then finally FIFA 19, which I'm sure you'll be aware of, is a video game, but is in itself just an abstract representation of somebody playing, perhaps coaching, managing a football match scenario. And all of these three things can be considered to be good examples of computing abstraction. Decomposition is one of the other cornerstones of computational thinking, and we can define decomposition outside of a computer science context for your own reference as the state or process of rotting or decay, something actually breaking down, if you like, and beginning to diminish. And in computer science, that context is not completely different. We still reference the idea of something being broken down, but it's not the complete diminishing of, it's more just the decompartmentalizing of a real-world object or concept into its core components. And we can, when we look at programming planning, for example, which we'll talk about a little bit more shortly, is we can actually see evidence of decomposition through the development of a high-level overview, which is a planning diagram which essentially allows us to structure the key components of a program that we're then going to go and be building. Here's an example for you of a high-level overview, and I've built this in and around the idea of a game of noughts and crosses. So put yourself into the position of a programmer who's looking to develop a noughts and crosses game. You'll notice at the top of this structure, we've put the name of the application, and then off of that you have your three main functions or procedures that will feature inside of that program. There'll be some sort of game board management, I'm sure there'll be a player management system, and then there'll be a movement manager as well. And inside of the movement management system, I've said or suggested that there will then perhaps be two additional functions or subroutines or procedures, and they would be perhaps the movement validation and the win game checking. Now, I'm not trying to suggest that this is the only way that this particular application could be programmed, not at all. This is purely just to show you how a high-level overview is structured and how decomposition fits in with that, in that it is the breaking down of and the representation of a concept using its key components. Algorithms, or the term algorithm, is the third of four cornerstones that make up this idea of computational thinking. And the definition of an algorithm in a real-world context is that it's a sequence of steps that can be followed to complete a task. And that differs just very slightly in a computer programming sense, whereby it's the applied use of those things. And we describe it as the process of implementing an algorithm into a specific programming language, for example, Python or VB.NET. And an algorithm is not a programming language. This is something I must stress to you highly when it gets to exam time, guys. You mustn't think of an algorithm as being a type of programming language. It's very much something that takes place in the design stage, and so it's something that we use to inform our programming, but algorithms are not considered to be a programming language as such. And there's two examples of algorithms for you there. I've put pseudocode and flowcharts. They are the main two. And pseudocode any exam question where students are given pseudocode will use the AQA standard version. However, when students are writing their own pseudocode, they may do so using any form as long as the meaning is clear and unambiguous. Now, this is something that's been taken for you from the official AQA specification. And what this summarises for you quite nicely is that if in your exam you're asked to write a piece of pseudocode, you can write a piece of pseudocode if you wish in more bullet pointed English. I would avoid the bullet points themselves, but you can write it in that sort of shorthand way, and the exam board is going to be quite happy with that, provided it is clear and unambiguous. So that's worth just referencing and bearing in mind as you go through this. There are some conventional rules for writing pseudocode, and those are things that you should be aware of. But ultimately, if you're struggling with those the day before you sit your exam, going with a shorthand version of sentences, of English writing, you're going to achieve something, because you are still documenting essentially that process that you're trying to represent in a clear and unambiguous way. The second form of algorithm that I wanted to talk to you about was flowcharts. Here I've got 1, 2, 3, 4, 5. I've got 6 different symbols here, and usually you're not going to need to use any more than these 6 symbols when you put together an algorithm, particularly at GCSE level. And I'm just going to go through these briefly with you. The first one is the rectangle, the process box, if you like, or symbol I should probably call it here, which is essentially used to state when something is happening in the program. It's the initiation perhaps of a particular section of code. It could be that something is taking place. Below that you've got a start and end point. It's fairly straightforward. This would appear both at the beginning and the end of your flowchart to signify a start and stop point. The arrow is the direction, which indicates where the program is taking you, the flow of the program. The connector is used if you run out of room. So if you're writing a flow chart on a piece of A4 paper and you run out of room, if you put a connector down as the next connecting symbol to your flow chart and put a letter inside of it, for example the letter A, and then you start at the top of a fresh sheet of paper, you put another connecting symbol down, also put an A in there, and then you just continue as you would. It's just a way of being able to extend a flow chart across multiple sheets of paper. You've then got the input or output parallelogram. And the input-output box is used to essentially state when perhaps a new value would be arrived or be arriving to the program, perhaps when a user has to input something to the program, equally when something is then being outputted, perhaps displayed to the user. And then below that finally you've got the diamond, which is the decision box, and this is what you would use to represent any sort of selection process or condition inside of your programs. Now, this is not my own. I do not claim to have any involvement in Lucidchart whatsoever, but Lucidchart is a piece of software that myself as a teacher will introduce to my students as a way of being able to construct algorithms using flowchart symbols. So if you decide that flowcharts are going to be your way to go in terms of writing algorithms, then Lucidchart is definitely worth a look. Again, it's not something that I have any attachment to whatsoever. It's just a resource that I've used for years alongside my teaching of algorithms, and so it might be something you find useful. The next diagram is used to represent one of the fundamental processes of a computer system, and that is the input process output storage diagram. Now, I would like to suggest that any computer system in the real world will feature at least 3, if not all 4, of these particular components. And I've said at the bottom here, examples, simple addition of 2 numbers or making a cup of tea. When we describe the input process and output situation, computer system if you like, more often than not you could model this around a real world problem to provide yourself with an example. And I'll start with the first of those 2 examples, the simple addition of 2 numbers. What we've got here is if you take the input, first of all, during this process, it's going to be the 2 numbers themselves. The process would then be to add them together, and the output would then be to give a result. Now, the storage side of things hasn't actually been used in this instance, but perhaps if you think of a computer, perhaps the one you're using today, and how the hard drive then sort of works in tandem with the computer system, you'll begin to appreciate where that comes in. Now, the feedback line that's then present on there as well does then suggest that actually, depending on what the output is, depending on what the purpose of this particular computer system could be, at times the output will then trigger a new input or provide something that reinforms the program itself. And so in order to complete this diagram, it's worth then adding that final line which shows a connection from output round to input, just to signal that actually at times this may be a repetitive system. It might be something that ongoes and continues to work even if once a single process has been completed. So that there for you is the input process output diagram. Now, I've got a past exam question for you. This was taken from one of the previous AQA GCSE exam papers. And on the left-hand side, you've got the question itself. And then on the right-hand side, I've just provided essentially what would be provided to you via the exam paper as well. It's a replication of the bottom part of that question where you've got the trace table. Now, admittingly, I haven't actually put the column headings in there of A, B or C, but I think you get the idea. And I'd like you to give this a go. Generally here, you've got a subroutine called total out, which is taking two parameters, both A and B, and then inside of the subroutine, A and B are being used in some way in order to carry out the workings of this particular subroutine. And I'd like you to pause this now, and I'd like you to give this a go. Ultimately, for those of you that are new to trace tables or a little bit vague on how they work, the idea here is to basically update the values for A, B and C on a new row whenever they change within the program. And it's quite possible that during one iteration of, on the screen there, the example while loop, it's quite possible that more than one value will change during the same iteration. And if that happens, then you can just put the new values on the same row, as it were, for each corresponding value within that table. You should only ever go onto a new row if it's a new value for a particular variable or value, or if it's a fresh iteration of some sort of iterative process within the program. So if you want to pause this, I'm going to be carrying on pretty much straight away. Please do that now, and then you can check your answers against what's followed. So I'm just going to talk you through this briefly. The question states that to complete the trace table below with the subroutine called total 3, 4 is being made. Now what that tells us is that A is going to be taking the value of 3 and B is going to be taking the value of 4. So we can straight away go and input the values 3 and 4 inside of our trace table. C is then assigned the value of 3 plus 4, or A plus B, and so we can assign that to be 7, and we can put that straight into our trace table as well. We then have the beginning of an indefinite loop, and while A is less than C, which it currently is because A is 3 and C is 7, we're then going to go and carry out the following two steps. We're going to reassign A the value of A plus 1, so we're essentially incrementing the value of A by 1, which is why we've now inputted A as being 4 on the next row, and during that same iteration, B is now being made equal to itself. Take away the value of A. Well, A has just been incremented to 4, so we're now taking 4 away from 4, which gives us 0. We then go back to the top of the loop to check our condition once again for that while loop, our Boolean comparison, and we're checking now whether or not A is still less than C. Well, A is still less than C because A is currently equal to 4 and C is equal to 7. So we're now going to go through that loop again, and we're going to reassign A another value, and that is going to be A being incremented by 1 again, so 5, and we're now going to do B is equal to B take away A. Well, A is equal to 5, so we're going to take 5 away from 0, which leaves us with minus 5. The next two rows you can see have been completed, and this continues up until A is being made equal to 7, and then the loop is completed once more. And what we can see here, up until the point of 6, it's completed once more until A is equal to 7, and then you'll notice that the while loop says while A is less than C, when A is equal to 7, it is no longer less than C, and so actually this continues no longer. And that is the completed version of that question. So hopefully that's been helpful. There's plenty of past exam papers you can access via the AQA website, as well as some sample papers. And so if you want more practice at that, either speak to your teachers or visit the AQA website yourselves.